Our context for the project is ultimately two different cylinders, or maybe the same cylinder observed at two different times. Now, if we in general have two cylinders, they might have different diameters. The outflow hole might be of different diameters. And it could be that you have a longer tube through which the water exits between one time and the other, between one cylinder and the other. Those are all variables that control how quickly the water descends in the cylinder. Also, of course, the water slows down. So, for example, now, if we have a water velocity indicated, let's say, by a purple arrow, okay, we have velocity here, and that would be velocity V1. And over here we have a velocity V2. Now, as I've depicted them, I think V2 is a longer vector than V1. If the water is descending in this cylinder more quickly than it is in this cylinder, and if this depth is less than this depth, as it is in this picture, then it's pretty clear that, intuitively at least, that the water flowing out of this cylinder will reach the outflow hole before the water in this cylinder. Okay, that this depth will always be ahead of this one. Now, that doesn't mean they necessarily started out the same, because this isn't necessarily our initial position. So if our initial position is higher in this cylinder than it is in this cylinder, so here's the initial position, here's the initial position, then it's entirely possible that this thing was descending faster initially than this one was, and that it's going to catch up. It's also possible that it wasn't all that much faster, and this one manages to get out before this one. So there are all kinds of possibilities. And we want to be able to analyze those in terms of the functions. So we have a depth function here, y1 of t, and a depth function, y2 of t. And then the rate of change of y1 with respect to time, we're going to call our v1 of t. And as it turns out, the rate of change of a depth with respect to time is how fast you're moving in the downward direction. And same here, it's how fast you're moving. It's actually, okay, well, there's a little bit of a fuzziness in that statement, but intuitively that's the way it feels. And we'll make it more precise. So, if y1 of t is a1t squared plus b1t plus c1, and the depth here is y2 of t equal a2t squared plus b2t plus c2, then what can we conclude? First of all, about the graph, and then about these relative speeds and what these relative speeds are telling us. So in general, we'll have a graph, let's just say t equals 0, that this one was this deep, and this one was this deep, and that they empty at different times. So this one is going to have a graph that might look like so. So this might be our y1 of t graph. That actually would be our y2 of t. And our y1 would start like here and maybe empty a little bit slower, so maybe the curve looks like this. Now, maybe having started lower, it doesn't empty that much slower, and it reaches its low point before this one reaches its low point, in which case this one would always be behind this one. Okay, this would always be lower than this one. And there's some details in the way I drew that might not make that so. But that's the general idea. Now, at any time, this graph will have a slope, and this graph will have a slope. There might be some time at which the slope of this graph is equal to the slope of this graph. For example, the slopes might be equal at this point and this point. So we want to look at the question of when are the slopes equal? And what is the difference in the depth? Now, there are many points at which the slopes could be equal. Okay, the slope could also be, well, we have a slope here that's kind of like this. Where's the slope of this graph equal to this? Well, it seems to be maybe at this point. And there's a difference in the depths for which we have equal slopes. Now, the way I've drawn it, there isn't that much difference in the depth here, but I'm not sure that's realistic. So we have to look at the equations and the mathematical behavior of these functions in order to determine that. And this is relevant to pressure loss in the outflow tubes, and it's relevant to reaching Mars in our hypothetical situation. And of course, if we don't reach Mars, we die, okay? So this is going to be very important. Okay, well, that's kind of an overview of where this analysis is really heading. We're going to have multiple depth functions, and we're going to draw conclusions about the relative depth functions and other aspects of these functions. The other thing I'll mention is that if y1 of t is this, left out a coefficient. That our v1 function, our rate of change of y with respect to t, is this. And we also have v2 of t equals 2a2t plus b2. Now, students who've had calculus, which would be linear algebra students who are taking it at least concurrently, and physics students who've already had it, we recognize these two functions as the derivatives of these y functions. Now, pre-calculus students will understand this as just the rate of change or slope function. But if you move on to an applied calculus course, this is going to become very important, and this kind of interpretation is going to become extraordinarily important to you.